Wanted to work through this example of a current carrying loop, rectangular loop that's immersed in a magnetic field. It's a uniform magnetic field. The arrangement is described in terms of a cube whose sides are 40 centimeters by 40 centimeters by 40 centimeters with one corner on the origin. In terms of that cube, one side of the loop, the top left side, is here. Another side of the loop opposite is downstairs here on the bottom right. And then there's two other sides of the loop that are made up of these diagonals across faces of the loop, the front face of the loop and the back face of the loop here. So we've got a loop that's carrying a current. One side of the cube upstairs, top left, is one side of the loop. One side of the cube downstairs, bottom right, is another side of the cube. And then diagonals on the front face and back face of the cube are the remaining sides of the loop. This loop is immersed in this magnetic field, and we're asked to figure out what the individual forces are on the four sides of the loop, and also the net force on the loop, and then finally the torque on the loop. And so that's the order that we're going to work through this problem. Before I do that, I want to add to the diagram. I've already added the current that's flowing in the loop is 5 amps. I've added the magnetic field that's in the loop is 0.02 Teslas. I want to add some of the dimensions in the problem. Specifically, I want to add the dimensions of the four sides of the rectangular loop. To help me with that, I'm going to label the sides of the loop 1, 2, 3, and 4. On the bottom right, I'm going to have side 1. On the front face of the cube, the diagonal, I'm going to have side 2. On the top left, I'm going to have side 3, and then the remaining side at the back face is side 4. And I'm going to write down the lengths of the different sides of the loop. Now, side 1 is just one of the sides of the cube. And actually side 3 is just one of the sides of the cube. And all the sides of the cube were 40 centimeters long. So L1, the length of side 1, is going to be the same as L3, the length of side 3. And they're just the same as the length of the sides of the cube, 40 centimeters. On the other hand, the front face, side 2, and the back face, side 4, those are longer because they stretch across the diagonal of the front face and the back face. So those faces are longer. By a little bit of geometry, L2, the front face, well, that's the same as L4, the back face. And because the diagonal makes up the hypotenuse of a right-angled triangle with these two sides of the cube, and that's true for both the back face and the front face, the diagonal is going to be root 2 times 40 centimeters. It's root 2 times 40 centimeters because the horizontal side here, that's 40 centimeters. The vertical side here, that's 40 centimeters. The hypotenuse then is the square root of the sum of the squares of those two 40 centimeters. So we got the square root of 40 centimeters squared plus 40 centimeters squared. So we got the square root of 2 times 40 centimeters squared, which is the square root of 2 times 40 centimeters. Okay, now I can go on and figure out the forces on these four sides. And I'm going to figure out the forces on these four sides using the field equation, the magnetic field equation. Magnetic field equation tells us the force on a current in terms of the current and the length of the wire in which that current is flowing, the magnetic field that current carrying wire is immersed in, and the angle between the direction of the current and the direction of the magnetic field. So let's go through one by one, applying the magnetic field equation to these four straight wires that make up the entire rectangle. So I'm going to start with wire number one. So we'll call that force number one for wire number one. By the field equation, it's going to be I, the current, and that's the current in every wire. So I won't label that with an index, times the length of the wire. That's L1. I will label that with an index because it's different for different sides. Times B, that's the magnetic field strength that we're immersed in. Don't need to label that. It's the same for every wire. Times the sine of the angle between the current direction and the magnetic field direction. And that will in general change. So in this case, the current is out of the screen, out of the whiteboard. The field is up the whiteboard. So they're at right angles to one another. So this is sine of 90 degrees. Okay, let's go ahead and fill in all the numbers now and see what the force is. We got 5 amps for the current in the wire. We got 0.4 meters for the length of the wire. We've got 0.02 Teslas for the strength of the field. And then we've got 1 for the sine of the angle between the current and the magnetic field. And if we calculate this product, I got 0.04 newtons. Now that's the strength of the field. What about the direction? Well, we can use the right-hand rule for the direction. So in using the right-hand rule for the direction, I'm going to point the palm of my hand in the direction of the current. So it's going to be hard for me to show that, but the palm of my hand is out of the whiteboard, out of the screen. I'm going to curl my fingers in the direction of the magnetic field, so that's up the screen. And when I do that, my thumb points from the right towards the left. So this is the direction. I've indicated it here on the sketch. This is the direction of F1. So it's actually in the negative X direction. So let me note that and just indicate it as minus X. Note also that it's at right angles to the magnetic field. It's at right angles to current. The magnetic force is always right angles to the current and right angles to the magnetic field. Second force is the force on wire number 2. This is the wire that crosses from the bottom right to the top left corners on the front face. Again, we can use the field equation for that. So F2, the force on wire 2, is the current, which no need for an index here. It's just the current in the current loop, times the length of this wire. Remember, it's longer. We denoted it L2, times the field that every wire is immersed in, times the angle between the current and the magnetic field. And in this case, that's 45 degrees. So the magnetic field is straight vertically upwards. The current is going both up and to the left. It's at 45 degrees to the vertical based on the geometry of the cube. And so the angle between B and I for the front face is 45 degrees. So here's sine of 45 degrees. And then we can plug in all the numbers here, plug in the plug in the electric current, that was 5 amps. Plug in the length of the wire. It was, I'm still going to write it as √2 times 0.4 meters. Plug in the magnetic field, 0.2 Teslas, and plug in the sine of 45 degrees. Now, the sine of 45 degrees is, I'm going to write it as a fraction here. It's 1 over the square root of 2. And the reason I wrote it like that is then we can see that this square root of 2 in the numerator, which is the extra length of wire 2 compared to wire 1, that's going to cancel with this square root of 2 in the denominator, which comes from the different angle, 45-degree angle of wire number 2 compared to wire number 1. If we cancel these quantities out, then all the other quantities are identical. We no need to redo the calculation. This is 0.04 newtons. We can figure out the direction of the field by the right-hand rule. The direction of the field, well, we're going to point there. Again, this is not going to make sense on the video. We're going to point the palm of our hand in the direction of the current. So that's from the bottom right corner to the top left corner. We're going to curl our fingers in the direction of the magnetic field, that's up. My thumb is pointing in towards the screen. And so this is F2. And F2 then is this is the Z direction out of the screen. So F2 is in the minus Z direction. Now, I could now walk through the other two wires. So there's wire 3 at the top, figure out with the field equation the force on it. Wire 4 at the back, the diagonal wire, figure out the force on it with the field equation. Or I can take a shortcut. And the shortcut is to spot the fact that wires 1 and 3 are really partnered. The partners in the sense that wires 1 and 3 carry the same size electrical currents. Wires 1 and 3 have the same lengths. Wires 1 and 3 are also in the same magnetic fields, and they're, interestingly, importantly, orientated such that currents flowing opposite directions in those magnetic fields. So the only difference between wires 1 and 3 is the reversal of the direction of the currents. And so the only difference in the forces between wires 1 and 3 will be the reversal of the direction of the forces. The forces wires 1 and 3 will be the same size by this argument, but the forces will be oppositely directed by this argument because the currents were oppositely directed. So while wire 1 experienced the force towards the left-hand side, then wire 3 will experience a force that's towards the right-hand side. So let me indicate that. And so I'm just going to write down the force on wire 3, the strength of the force here is what I'm talking about, is going to be the same as the strength of the force on wire 1. And that was 0.04 newtons, but the direction is going to be the opposite direction. So for wire 1, the force was in the negative x direction. This is going to be in the positive x direction. The same arguments apply for wires 2 and 4. They're also a pair. So they both carry the same current. They both have the same length. They're both immersed in the same magnetic field. The only difference is that the currents, the directions of the currents are opposite in wires 2 and wire 4. So if the currents are opposite, that means that the forces are opposite. So the force strength on wire 4 is the same as the force strength on wire 2, but the force direction on wire 4 is opposite the force direction on wire 2. So if we look here, F2 was in towards the screen. It's a little hard to draw this, but F4 is going to be out of the screen. Let me write down then the strength of the force. So the strength of the force on wire number 4, we've argued, because the only thing that happened was the current reverse from wire 2. This is the same strength as the force on wire 2. That's a 0.04 newtons. The direction of the force is going to be opposite the direction of the force on wire 2. The force on wire 2 was in the negative z direction. This is going to be in the positive z direction. Well, now we've got the answer to the 4 individual forces, both their magnitudes and their directions. And actually, all the magnitudes were 0.04 newtons. And then the directions were sort of pairs of directions, a pair of forces in the z direction and a pair of forces in the x direction. We can add up these forces. I think you know what's going to happen here, but let's go through the procedure of adding up the forces. Let me do it how I would do it in general. So in general, if I wanted the resulting force on the rectangular loop, I'd want to compute it by thinking of its components in the x direction, its components in the y direction, its components in the z direction, adding up all the individual force components in the x, y, and z directions to get the total force in the x, y, and z directions. So let's do that for the x direction. So the resulting x component of the force on the entire loop is the sum of all the individual x components of forces on the wire loop. There are two of those. One of them is due to force number one on wire number one. That was in the negative x direction. And the other one is from wire number three. The force on wire number three is in the positive x direction. So I've got to add F1 and F3. F1 is in the negative x direction. F3 is in the positive x direction. And the strengths of F1 and F3 are both 0.04 newtons, so minus 0.04 newtons for F1 because it's in the negative x direction, and plus 0.04 newtons because for wire 3 it's in the positive x direction. And of course, minus 0.04 plus 0.04 is going to be 0. There's no force in the x direction. The two forces cancel each other out. The same is true. Let's take the z direction. The z direction also has two forces acting in it on the wire on the front face and the wire on the back face. The wire on the front face, the force is in the negative x direction. So I'll indicate that as minus F2, the minus being negative z direction. The wire on the back face is in the positive z direction. So I indicated that as plus F4. And then I can fill in the numbers. So I've got minus 0.04 newtons plus 0.04 newtons again. All the forces were the same side. Again, these add up to 0. So there's no net force in that direction. Finally, well, we've figured out there's no net force in the x direction. There's no net force in the z direction. None of the individual forces had any components in the y direction. They had no components in the y direction because that's actually the direction of the magnetic field. And the force is always perpendicular to the magnetic field. So it has to be in either the x or the z directions. So for all those reasons, Fy must be 0. And so we actually have a total force that is 0 because it has no x component, no y component, no z component. The total force on the entire loop cancels out. It's not going to start accelerating towards the left or the right, out of the page or into the page. It's got no net force acting on that loop. The last part of the problem asks to figure out the torque on the loop. So the way we're going to figure out the torque on the loop is that equation that describes the torque on a loop in a uniform magnetic field in terms of a quantity called the magnetic moment of the loop and the magnetic field that it's immersed in. And that quantity called the magnetic moment of the loop depends on the geometry of the loop, specifically the cross-sectional area of the loop, depends on the current that happens to be flowing around the loop. So that's how we're going to figure out the torque. I've run out of space down here. I'm going to write the answer for the torque upstairs here. The master equation for us, T tau, is the torque. That's our symbol for the torque. It's equal for a magnetic torque, the special case of a magnetic torque, the product of mu, the magnetic moment, times B, the field that's creating the torque. These two things have directions to them. The sine theta is the sine of the angle between their two directions. So this is the equation that we're going to use. Now, we want to figure out the product of the magnetic moment, the magnetic field, and this sine theta. So to do that, we better first remind ourselves of the magnetic moment and remind ourselves also of the ingredients in the magnetic moment. So let me just do that. I'm going to add to this annotation up here on the left-hand side of the screen. So the magnetic moment size in general is the number of turns of your loop times the current flowing in the loop times the area of the loop. So that would be the general equation for the magnetic moment. And in our case, there's just one turn in the loop. So the magnetic moment will just be IA, the current times the area. The area, well, that's the area enclosed by the loop. Now that loop is this cross section here. I'm going to change colors, I think, because it's going to help me a little bit. I'll change colors to green here. This is my cross-sectional area of the loop. And so the size of A that describes the loop is going to be, in this case, the width of the loop. So that's either this top left side or this bottom right side times this this kind of height of the loop here, which is the hypotenuse of this right angle triangle. So it's going to be 40 centimeters times the square root of 2 times 40 centimeters. So this is going to be the square root of 2 times 40 centimeters squared. That's the area of the loop. And then the direction of the loop is at right angles to the face of the loop. That's our rule for drawing the direction. So there's a right angle in here. And so it's pointing upwards and it's pointing towards the right. It's actually at 45 degrees to the vertical. So the other piece of information here is that theta, the angle between the magnetic field and the area vector. So the magnetic field is straight vertically upwards. The area vector is 45 degrees to that vertical. And so this is 45 degrees. So there's a little bit more geometry, a little bit more of reminding ourselves about magnetic moments, but these are going to be ingredients in this calculation here. So we can now fill in the magnetic moment, fill in the field, fill in the angle between the two of these quantities with directions. So let's go ahead and do that. Magnetic moment is the current, that's 5 amps, times the area, that was root 2, times 0.4 meters, and that's squared. And then that's times the magnetic field, that's 0.02 Teslas. And then that's multiplied by the sine of this angle between B and A. That's sine 45 degrees. So here I've filled in all the quantities in this this equation here for the magnetic torque. And if I multiply them all out, we might remember that this is 1 over square root of 2, and it will cancel this square root of 2 here in the numerator. And so we just got 5 amps times 0.4 meters squared times 0.02 Teslas. And that came out to be 0.016 newtons meters. Those are the units of torque. Anyway, that was an example, an illustration of a rectangular loop in a uniform magnetic field. We explored the forces on the sides of the loop. There were forces on every side of the loop in this particular example. We explored the net force that's acting on the loop. We discovered in this uniform field, the forces add up to 0. And then we figured out the torque. We figured out that actually there is a torque that will tend to turn the loop. And you can see that if you look at the picture. Think about this axis here. Think about the action of this force on side 3 at the top left. Think about this force on side 1 at the bottom right. They're kind of doing this. And so that's going to turn this loop between those two sides. And so the loop will rotate, and it will rotate in this direction, clockwise in our sketch.